At this very moment, a force is holding you to your chair, tethering Earth to its star, and choreographing the waltz of 100 billion galaxies. And that same force is so fantastically, so embarrassingly weak that you can overcome the gravitational pull of an entire 6,000 trillion kilogram planet with a 10-gram refrigerator magnet. This isn't just a party trick. It's a cosmic crime scene, a profound and disturbing glitch in the matrix of reality that has haunted physicists for nearly half a century. Textbooks call it the hierarchy problem, but that sanitized name hides a chasm in our understanding. It's a whisper that the standard model of particle physics, our greatest intellectual achievement, is built on a foundation of impossible coincidences. To grasp the sheer absurdity of this, we need to meet the other forces. First, the strong nuclear force, the universe's unbreakable glue. It binds quarks into protons and neutrons with such ferocity that if you could scale it up, its grip would be equivalent to a force of 15 tons. Then there's electromagnetism, the artist of our world. It's 100 times weaker than the strong force, yet it's what forges atoms into molecules, paints the sky blue, and carries the light of distant stars to our eyes. Next, the weak nuclear force, the agent of change. 100,000 times weaker still, it governs radioactive decay, allowing stars to burn and creating the heavier elements that make life possible. These three forces operate in a sensible, tiered relationship. They are different, but they are relatives. Then there is gravity. It is not just weaker, it is an alien. It is a ghost. To be precise, gravity is roughly 1,000 billion times weaker than the strong nuclear force. That's a 1 with 39 zeros after it. There is no other hierarchy in known physics that spans such an incomprehensible gulf. It's like comparing the mass of a single virus to the mass of the entire Milky Way galaxy. This isn't just a numbers game, it's a question of naturalness. In physics, parameters should not require absurd fine-tuning to work. Yet, the mass of the Higgs boson, the particle that gives all other particles mass and effectively sets the scale for the electroweak force, is a perfect example of this unnaturalness. According to quantum field theory, the Higgs should be constantly interacting with a sea of virtual particles that pop in and out of the quantum foam. These interactions should contribute to its mass, and calculations suggest they should drive its value up to the so-called Planck scale, the natural energy scale where gravity is expected to become as strong as the other forces. That's about 10 to 19 giga-electron volts. Yet, when CERN discovered the Higgs boson in 2012, its mass was a paltry 125 giga-electron volts. For our universe to exist as it does, the bare mass of the Higgs and the colossal quantum corrections must cancel each other out with a precision of 1 part in 10 quadrillion. It's like finding a pencil balanced on its tip and having it stay that way for 13 billion years. It's possible, but it screams that we are missing something fundamental. For decades, the leading contender to solve this puzzle was supersymmetry, or SUSY. It proposed a beautiful new symmetry in nature, where every known particle has a heavier superpartner. These new particles would contribute to the Higgs mass with the opposite sign, elegantly and naturally canceling out the enormous quantum corrections. Physicists were so sure of it that they expected the Large Hadron Collider to light up with evidence of sparticles, squarks, and selectrons. But after more than a decade of smashing protons at nearly the speed of light, the LHC has found nothing. The silence from Geneva has been deafening. The beautiful solution has failed to appear, leaving the hierarchy problem more stark and more troubling than ever before. The pencil remains balanced on its tip, and we have no idea why. This forces us to confront a more radical possibility. We have always assumed that gravity is intrinsically weak. We have measured its constant g and plugged it into our equations, treating it as a fundamental property of the cosmos. But what if that's our mistake? What if gravity's inexplicable weakness isn't a property at all, but a symptom of a grand deception? What if gravity only weak to us because we are only experiencing a tiny fraction of its true power? What if the force that binds the cosmos isn't playing by our rules because it's not entirely? From that paradox of a ghost-like gravity emerges one of the most audacious, mind-altering proposals in the history of science. It suggests that our entire three-dimensional universe, everything you've ever seen, touched, or known, from the smallest quark to the largest supercluster of galaxies, is nothing more than a thin membrane, a 3D brane, floating within a vast, higher-dimensional reality called the bulk. This isn't just a metaphor, it's a concrete physical model first proposed in a landmark 1999 paper by Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali, and refined in parallel by Lisa Randall and Raman Sundram. In this brain world scenario, the particles and forces of the standard model, electrons, photons, quarks, gluons, are all permanently stuck to our brain. In the language of string theory, they are the endpoints of open strings, and those endpoints are forever anchored to our dimensional sheet. They can move left, right, up, down, forward, and back, but they can never leave our 3D prison. But gravity is different. Gravity, in Einstein's theory of general relativity, is not a force in the same way as the others. It is the curvature of space-time itself. In string theory, its carrier, the graviton, corresponds to a closed loop of string. With no endpoints to anchor it, the graviton is a free agent. It is not confined to our brain. It can and does travel freely through the higher dimensional bulk. This provides a stunningly elegant solution to the hierarchy problem. Gravity isn't weak. Gravity is colossal, perhaps as strong as the other forces. But its strength is diluted. Most of its influence radiates away from our brain, spreading out into the vast, unseen dimensions of the bulk. The gravitational pull we feel is merely the faint, leftover whisper of its true power, the tiny fraction that happens to intersect with our reality. It's like hearing the faint bass from a concert happening in the next building. You know there's a powerful source nearby, but you only perceive a pale imitation of its full intensity. Suddenly, gravity's weakness is no longer a fine-tuning problem, but a simple consequence of geometry. This isn't just armchair philosophy. The brain world hypothesis makes concrete, testable predictions. If these extra dimensions exist, they could be detected. The ADD model, for instance, suggests the dimensions could be as large as a millimeter across. While we can't perceive them, gravity can. Newton's inverse square law, which states that gravity's pull weakens with the square of the distance, has only been rigorously tested down to about 50 microns. Below that scale, in a world with large extra dimensions, gravity would leak more rapidly and its pull would drop off much faster than predicted. In laboratories around the world, like the Eote Wash Group at the University of Washington, physicists are running incredibly sensitive tabletop experiments using torsion balances, essentially miniature high-tech versions of the one Cavendish used in 1798, to probe gravity at these microscopic distances, searching for any deviation that would signal the presence of the bulk. An even more spectacular test could happen at the Large Hadron Collider. If two protons collide with enough energy, they could, for a fleeting moment, create a graviton with enough momentum to knock it clean off our brain. To our detectors, this would look like a terrifying violation of one of physics' most sacred laws, the conservation of energy. The energy after the collision would be less than the energy before. But it wouldn't be gone. It would have escaped. It's the only force that can escape, and the signature of its departure, a jet of particles recoiling against nothing, is something that experiments like ATLAS and CMS are actively hunting for. In some extreme versions of these models, the collisions could even have enough localized energy to create microscopic black holes, which would evaporate almost instantly in a unique shower of Hawking radiation, a definitive sign of new gravitational physics. The consequences of this idea ripple through all of cosmology. What is dark matter, the invisible scaffolding that holds galaxies together? It could be composed of Kaluza-Klein particles, the ghostly echoes of normal particles vibrating in the extra dimensions, which we can only feel through their gravitational influence. What is dark energy, the mysterious force accelerating the expansion of our universe? It could be the energy of the bulk itself, or a repulsive force between our brain and another parallel universe floating nearby. The implications are almost too vast to hold in the mind. Our universe, which we thought was everything, may be just one page in an infinite book. Other brains, other universes with potentially different laws of physics could be floating less than a millimeter away from us in the bulk, forever hidden from our sight, their existence only betrayed by the faint gravitational whispers they send across the void. The search for gravity's missing strength, then, is no longer just a quest to balance an equation. It is a search for a hidden door, a door to a reality larger, stranger, and more profound than we ever dared to conceive.